So today we are going to talk about determinants of the product of matrices, inverses, and matrix transpose. These are topics that we ignored and left out as much as we could so we can focus on solving a linear system of equations. So today we are going to learn more about these topics and fill some of the gaps that we left previously. Now, another reason to go through these topics is because hopefully we'll see some of the reasons why we were saying, for example, if the determinant is not 0, we can solve the system. We gave you as a fact, but as we discuss the connection between, for example, matrix inverses, that should make more sense after today. Now, but the major topics that we want to cover today is that the determinant of two matrices, if we multiply them and then take the determinant, is the same as multiplying their determinants. That's a very handy result in linear algebra. And we want to give a definition to the inverse of a matrix. What does it mean to have an inverse for a matrix? And we also want to reiterate that even though that exists for certain matrices, you rarely want to compute it. We don't have enough motivation most of the time to compute the matrix inverse. And we'll see some easy formulas. For example, this is for a 2x2 matrix. Pretty much that's the only inverse that you want to do by hand. Beyond that, we usually don't do hand calculations. And we also want to learn the transpose of a matrix. All right, we start with this useful fact that if I give you two square matrices and you multiply them, and then I ask you what's the determinant, it is the same as taking their determinants before multiplying them and then multiplying the determinants. Now, the determinant is a function that maps a square matrix to a number. If you remember, that's how we defined it. So when I talk about the determinant here, for example, I'm talking about multiplying numbers, real numbers, right? So these are not matrices. This is just an example. Now, there are several ways to prove it. We are not going through those. If you're interested, that's a good topic to talk about it outside of the lecture. Now let's think about that fact and LU factorization. If I calculate the LU factorization of a matrix and then we want to take the determinant, what happens? I have A, and A is LU. Based on what we just learned, we should be able to write the determinant of A is the determinant of L times the determinant of U, right? Is this interesting or not? It is? You're very excited. Can you give us a reason why you're so excited about this line? So you remember that we learned that the determinant of a triangular matrix is just the product of its diagonal. That's exactly the reason this is exciting, because now it looks like no matter what's the size of A, we have a way of calculating its determinant by just factorizing it using LU. That's a good, basically, tool that's been enabled by this property of determinant and LU.
Isn't it that one, I don't remember which one, I think it was L, that the diagonal is always 1? Or is it U?
Right, the question is, isn't the diagonal of L, the way we basically calculated it, always just once? That's right, because we were normalizing with pivot, which in fact most of the time should make the determinant of L just 1. So we really care about the determinant of U. Right, you're right, because this is most of the time, in the way we calculate it, is 1, right? Which also, that highlights the examples that you remember. Suddenly we would get a 0 on the diagonal of U. That would just completely destroy the determinant, right? Collapses everything to 0. So it's after decomposing this matrix to L and U, it's so easy to see what's going on underlying the determinant and knowing a few useful facts in linear algebra. So the determinant of A is just the determinant of L times the determinant of U. Now, as a reminder, just to recap, we learned that if a matrix is a lower triangular matrix, the determinant is just a product of its diagonal interarrays. That's the example we had. Now, the same thing was true for the upper triangular matrix. So in the end, it doesn't matter if it's a lower triangular or upper triangular. As long as it's a triangular matrix, the determinant is the product of its diagonal entries. So this is another reminder for the upper triangular matrix. And in fact, now we are able to calculate the determinant of any square matrix. Right? Remember, the determinant is only defined for a square matrix. So for any square matrix, we can decompose it into L and U. And LU with row permutation, we already know that it always exists, even if the determinant is 0. And we can, in fact, see why it's 0. And then we can calculate the determinant through some straightforward multiplications. All right, that's all good, but if you remember, we had, in the end, we said LU that we learned by the idea of peeling the onion, that was a little simplified. So we had some special cases when the pivot could be 0 or C could be an entire column of 0. And then we settled for the idea that if we use row permutation, that's necessary and sufficient for decomposing any matrix. So what we ended up with was LU with row permutation. So we had P times A. P is a permutation matrix, exchanging rows of our original matrix, equals LU. What can we say about this? Or at least where can we start to explore what can we get out of this based on what we learned so far? Looking for ideas?
We can start with the determinant by splitting up.
Right. How about we take the determinant from both sides and then just, instead of thinking about it, right, doing some calculations, see where it leads. I do that all the time in my research. Usually something good comes out. Then I try and make sense of it. So if we say, we take the determinant from, if two sides of the equality are the same, if you take the determinant, right, it should be the same. Why we can do this? This is why is that I can do this? Then that's still okay. Okay, before that, I clarify a question in chat that I said row permutation is sufficient, is the necessary and sufficient, right? Maybe you heard insufficient, but it is sufficient condition. So it's enough to decompose any matrix. Because there are other ideas like column and row and column at the same time, you can make it a little fancier, but just row permutation is enough. Now, remember equality, you remember we had an example in Julia when we said double equality sign, whether two sides are equal. That means that every entry of the, first of all, they have the same size, and every entry of the left-hand side is the same as the corresponding entry of the right-hand side. So essentially, two matrices must be the same. So the determinant must be the same too. So it's okay to basically take the determinant on both sides. I'm just applying the same function to both sides. All right, I can, based on the fact that we learned, I can factor the determinant of the product to the product of the determinants. Now from here, it sounds like I can conclude that the determinant of A is same as before, the determinant of L times the determinant of U divided by the determinant of P. Now, this is a little concerning because what if the determinant of P becomes 0, right? Then it's not defined. That's a little counterintuitive because if L and U, right, they don't have zeros on the diagonal, we expect the determinant of the matrix A to be available and be non-zero. And I'm exchanging some rows. Can this lead to making the determinant degenerate or undefined? Is that possible? Yeah? So one answer is, yeah, it can happen if the determinant of P is not well-defined, it's 0. It's defined, it's basically 0. Now that would be very disappointing, right? But fortunately, so the equation is correct. We have, there's nothing wrong with this equation, but we need to have a condition the determinant of P to be non-zero. Now, we don't have a way to enforce it really at this point. But what we can do is looking into the nature of the permutation matrix, right? So in a generic case, it's not giving us any information, but we need to look into the structure of P, see if we can make any conclusion that this won't be 0. Okay, so that's the idea here, and it turns out that we can do that. I'll give you as a fact now. In the end of the lecture, you'll see why it's like this. So it turns out that the determinant of any permutation matrix, of course, square, is either 0 either plus or minus 1. It cannot be any other number. So it can be negative or positive, but it's always 1. Or you could say its absolute value is always 1. This is great news because it will not interrupt our calculation. So it doesn't matter. It's not going to change the value up to 1 sign. We might get different answer, and then we need to compensate that using the determinant of p, which will, if it will be positive, there is no change. If it's negative, it will be a change of sign. Now, it will be a change of sign to apply and correct it, because remember, when we exchange rows of A, the corresponding rows of L are also exchanged. So this sign changes for compensating that. Generally speaking, exchanging rows in a matrix will result to negating the determinant. That's a more general topic, but we care about the permutation matrix at this point. Okay, so we moved all the way to the end. Let's look into an example. I have a 3x3 matrix here. I have no idea what's its determinant. I am going to factorize it into L and U. Now, I'm not doing it using permutation because actually, if I just do the simplified version of LU, it works. So I get L and U. Let's say this is our hand calculation. And what is the determinant? Just like we said previously, that we have 1s on the diagonal of L. So the determinant of L is actually 1. 1 times 1 times 1. And U is minus 2 times 5 times minus 4. And that makes it 40. Okay, so what I'm going to do right now, this was my hand calculation. So what I'm going to do now, I want to use LU with permutation in Julia, and then I should be able to get the same answer. Okay, so I want to make sense of that coding with my hand calculation. So I load linear algebra library. I define my matrix A. I pass A to the LU function of Julia. I get an object f.L, if you remember, that's how we call the attribute of that object. @ show is just showing the output of each row. It repeats the line also, it shows the output. So the determinant of L is 1, that checks out. The determinant of U, however, is negative, and the determinant of P is also negative. So whatever happened, which last time we talked about it, you can look into permutation and then see what happened inside row exchanging that will be reflected in L and U. That resulted in a negative determinant for U. Now, if I say determinant of A equals 1 over minus 1 times 1 times minus 39. So this gets canceled together, and I get almost the same answer. Right? This is, I have here 39.99999 forever. If you can forgive numerical errors, that's pretty much 40, right? So be careful when you use these facts when you are coding, because now you might think that I'm just doing LU, but then your algorithm is actually doing permutation, then you need to take that sign into account too. But generally, we just verified the determinant of the product, which, by the way, in this line, I'm just directly getting the determinant of A, right? So if multiply these two and divide it by the third one, you get the same answer as directly querying determinant of A in Julia. Okay. Any questions so far? Before jumping to the next topic? Is it too easy? There's a good challenge today. Let's see if we can solve a challenging problem that will show up. A lot of graduate students might not know that, but we will talk about it today. How do I know? Because I grade their codes in a graduate class. And when I see they use matrix inverses directly, I want to pull my hair and give them zeros. But I don't do that because they have to graduate and go make money. So it's very difficult to, I think, teach them to not do it because I think they never learned it in undergrad. What you learn here stays with you, I think, for a long time. All right, so let's talk about the identity matrix. Once in a while, we popped up a matrix, say it's all 1 in the diagonal. Everywhere else is 0. We call it the identity matrix, and we used it, but we never formally defined it. So now we want to talk about it, and what does it mean to have an identity element for matrices? So generally, the identity matrix is a square matrix that has 1s on the main diagonal, or the diagonal, and 0s elsewhere. Now, just like LU, you can define a rectangular identity matrix too. Obviously, it won't look perfect 1s at the diagonal, but that's not a standard. It's something that you can usually do in Julia or MATLAB, or maybe you're doing some calculation that is convenient to define it that way. When we say an identity matrix, we mean a square. Here are some examples. 1 by 1, which is just a number, a scalar. And it's only 1. 2 by 2. 1s on the diagonal, 0s everywhere else. 3 by 3. 4 by 4. Do you want me to write down 5 by 5? No? You're already tired of it. So that's the idea. So whatever is the size, fill in the diagonals with 1s, and then 0s everywhere else.
Since technically this is a lower, or is this a lower triangle or an upper?
Good question. Is this a lower triangular matrix or upper triangular matrix? Yeah, neither of them, right? Both of them. So, because if you remember some of the examples, L ended up being the identity. which was the ideal case because the problem is already solved. If it's the identity, you can read the variables values. So it's both of them.
How will the determinant ever be negative then, unless you have a -1 inside of that identity matrix? Because can't you just do the determinant, which would be the diagonal?
It's reflected in U. That's why in Julia. So the question was, how can it be negative if? So the answer to the previous one was that a diagonal matrix is both lower triangular and upper triangular. We're not making an exception because definition was that whatever is above the diagonal should be 0, whatever is below the diagonal should be 0, and it satisfies both conditions. So it gets both properties. Now, the second question is that how can this have a negative determinant if it's always like this on the diagonal? And the answer was that because the row exchange affects exchanging rows in U. So in the Julia example we had, it was U that had negative sign. So it was reflected there. So L was actually 1, right?
But isn't the determinant of P still the -1? Like, how does it become?
Okay, so let's clarify what's going on. Determinant of A is 1 over determinant of P times determinant of L times determinant of U. Now this will give us 1 over -1 times 1 times, I'll just call it 40. Sorry, it's minus 40, okay? So this should give us 40, right? Yeah. So it's the sign of P that is canceling that negative sign in U. Because both of them have the same row exchange, P and U. So both of them get negative sign, and then they cancel each other.
But what I'm wondering, like, if for P, like, if it gets rotated, because then it's no longer a triangle matrix, I guess.
Yeah.
Okay, that's what I was.
So the sign change will be together, so they always cancel each other, right? And if it's positive, they're positive together. Now there is extra facts that if the number of row exchanges are even, the sign is positive. If you exchange rows odd number of times, then you get negative signs. That's why it's happening. That's just another extra fact. You don't really need to think about it now. And in fact, you don't need to really think about it. It's just built into the equation we wrote. It's just there. They get canceled together. But it's important to know. Now let's we can also verify. So remember, P was, so I, the identity matrix, 2 by 2, is like this. Now the determinant of a 2 by 2 matrix was easy. We had a formula for it, right? Now, although it's diagonal, we know there's an easier formula, but our formula was that 1 times 1, right, minus 0 times 0. 1, which is the same as just multiplying the diagonal elements. Now, if I build a permutation matrix by exchanging first and second row, this is what I get, right? What is the determinant of P, my permutation matrix? Zero. So we had A, B, C, D. It was A, B minus C, D. No. It was A, D minus B, C, right? So we have 0 times 0 minus 1 times 1, negative 1. So I did one time row exchange. It changed the sign to negative 1. If I do one more time, well, it goes back to the identity. But if you make the matrix bigger, you will have more configurations to play with. You can try. You do odd number of times, it's always negative. If you do even number of times, it's positive. So it's just a property of this permutation matrix, the way it's defined. Now, a note on the notation. We usually show the identity matrix using I, right? The initial of the identity. Sometimes to emphasize that what is the dimension size of the matrix, for example, if it's n by n, we write I subscript n. So I2 means 2 by 2. Now, why I don't write 2 by 2? Because it's redundant. It's a square. It's just cleaner to write it as 2. Now, sometimes it's clear from the context what's the dimension. You might see people just dropping it, just being lazy and just write I. If it is clear from the context, it's okay. But if it's not, it's better to use a concise notation. Now, what's the role of an identity element? Now, this is a multiplicative identity. You remember when you work with real numbers, when we have the additive form, the additive identity is actually 0, right? You have A plus 0 will give you A, which is commutative because you have 0 plus A is still A. We are talking about multiplicative identity. And it's not just a number. If it was a number, we could say A times 1 equals A. 1 times A equals A. And in fact, it's true for 1 by 1 matrices, just scalars. Now, we are talking about matrices. It's no longer, in general, commutative. And we are going to define it for a rectangular matrix. Suppose A is a rectangular matrix with m rows and n columns. If I is an n by n identity matrix, because A is m by n, I can multiply the identity matrix from the right side of A, and the result will be A. So it leaves A identical to what it was. So that's the role of an identity element, which is very useful later when we want to define the inverse. We need that. Can I also do this? I'm shaking heads, angry faces. No, we can't. What should I fix here?
Sorry. You need to have the columns of the leading matrix match up with the rows of the second one, so you have to make that instead.
Exactly. You're right. The columns of, you said, the leading matrix should matches the rows of the second matrix. So I need to, if A is rectangular, I need to take an M by M identity if I want to multiply from left. So now if A is a square, then it doesn't matter. Both sides will work just fine. Now we have more examples. If you go to example 6.2 in the book, you can read more about it. But I think the idea of the identity matrix should be clear here. Now that we learned the identity element, now we are able to define the inverse of the matrix. Suppose we have an n by n matrix, A. We say A has an inverse if A inverse multiplied from both right and left gives you the identity matrix. Now A is n by n squared. The inverse of it is also n by n. You can multiply from left and right. It gives you an n by n identity matrix. So the definition says that it doesn't matter from left or right. A matrix commutes with its own inverse. You can multiply from left or right, you get the same answer. Which is pretty special. The inverse of a matrix is very special because matrix multiplication is non-commutative. This rule does not work in general. If this holds, then we say A is invertible. Okay. Which also brings up the question that does it exist always, right? And I'm saying if it holds A is invertible, then when is the case that A is not invertible? That's what we're going to see. Now before that, I claim a matrix has an inverse. If a matrix has an inverse, it's unique. That means that there's only one of them. Now, if A and B are both n by n, and it happens that A times B equals B times A is the identity matrix, then B must be the inverse of A. There is no other explanation, okay? It is unique. The proof is quite straightforward. Here is one idea. Now, suppose A inverse, right, is the inverse of A, and B is another inverse of A. That means I have two of them, and they're not necessarily the same, right? Now, from the fact that A times A inverse must be the identity matrix, right, I can start from here. Then I multiply both sides by B. I'm allowed to do that because that must be defined. B is just another inverse of A. Now, by the very fact that B is inverse of A, B times A must be the identity, right? And identity times A inverse should give me A inverse again. Likewise, B times the identity should give me just B. So I reached to the conclusion that I didn't want, I did not assume that's the case, but the conclusion is that A inverse must be equal to B to satisfy that condition that a matrix commutes with its inverse, and A inverse times A equals A times equals the identity, right? I'm using this fact to prove it. It's a little twisted. If you have a question, I can explain it again. But this seems to be a straightforward to show the uniqueness of the inverse of a matrix. Yeah?
What is the B exclamation point again?
That's the surprise that we are facing here. Not everything is math. You can ignore it. Not factorial. It's quantum inverse of a matrix. So that's the exclamation mark. That's not math. If you hear me again. There's a question on chat. Is there an example with matrices and numbers? I do have an example here. Let's see if that's what you mean. 2 by 2 matrix. We know the determinant is A times D minus B times C. We don't want it to be 0. And we had a formula for inverting it, which ends up being the 1 over the determinant of A. That's why we don't want it to be 0. Times this matrix, DA minus B minus C. So what happened? A and D got exchanged. B and C changed sign. And they're divided by the determinant. Why we should believe this is the inverse of A? Is it okay if somebody shows up and says this is the inverse of A? If you can show it is, that's okay, right? You maybe make a guess, and maybe your guess is right, as long as it's verified. Because if it works, we just proved that it's unique, right? Then good for you. That was a good guess. That's okay. So we can, let's try A, B, C, D. I'm going to just first multiply these two matrices. I get A, D, minus B, C. I get minus A, B. It's harder than I thought. Help me. I'm doing this. Maybe I should do the other way. But anyway, I was doing row by column. So A times D plus B times minus C. I have minus A times B plus, okay, now makes sense, plus B times A, right? Which makes it 0. Now we have, right, C times D minus D times C. Makes this one 0, 2. And then we have minus C, B plus A, D. It was a little embarrassing, but we got there. And this should be divided by AD minus BC, okay? Divided by AD minus BC. It's the same thing we see here, right? So this will result to 1, 0, 0, 1. Now, it turns out it works. You can do it the other way around to check. Sounds like it's the inverse. As long as we can calculate this division and the determinant is not 0, we can evaluate it. And by the fact that we just proved that the inverse is unique, then this must be the inverse of a 2 by 2 matrix. Now, a numerical example. Let's say I have a matrix 4, 2, 5, 3. I want to invert it. The determinant is 12 minus 10, right? 2, which I see here. And I'm just using that formula to change the location of A and D and negate B and C. Let's verify it in Julia. I define A and I define B based on what we just calculated using hand. And I'm calculating A times B and B times A. And both of them, they're giving me an identity matrix. So just a sanity check to convince ourselves that that's correct. All right, so very important fact to put things together so far. Now we learned that the product of the determinant of product matrices is the product of the determinant. We learned that A times A inverse equals the identity matrix. And we can, of course, take the determinant of both sides. Now, if we do that, what do we get? The determinant of the identity matrix is 1, okay? And this is the first fact we learned today. Now we get an equation that tells us the determinant of A multiplied by the determinant of A inverse must be equal to 1. And the only explanation here is that first of all, if two things are getting multiplied and the result is 1, they cannot be 0, right? If one of them is 0, that just doesn't make any sense because the other side of the equality must be also 0. Now, from here, we can also conclude that the determinant of A inverse is just 1 over the determinant of A. So if we know the determinant of A, we can just calculate its reciprocal. We don't need to go through the whole calculation for A inverse. Now, what's the implication here? We're saying that if we multiply them, the answer must be 1. On the other hand, the determinant must be non-zero for the determinant of A inverse to exist. Otherwise, we get division by 0 here. So we can say that if the determinant of A is not 0, then A has an inverse. Or we can say A inverse exists. So that's a reasonable conclusion from here, right? Because if the determinant is 0, then this equation breaks down. So putting what we observe together, we get this fact that an n by n matrix A is invertible if and only if the determinant of A is not 0. Or you see sometimes if and only if is like this. IFF. If and only if means if A is invertible, the determinant is not 0. If determinant is not 0, then A is invertible. You can go both sides, both ways. Now this is very important because previously we defined that A, when we're solving a linear system, the determinant must be non-zero. And now we learned that when the determinant is non-zero, that means we can invert the matrix A. Sounds like there's a relationship between inverting matrix A and solving the linear system that we will see today. Before that, a lot of facts today. We're verifying some of them. Maybe Jesse organized a trivia for you instead of final exam and give you Rob 101 t-shirts maybe. Maybe that's what we should do. Replace final exams with trivia. Then half of the class can pass. What should we do with the other half? Shrugging. You don't know, they can figure it out. Maybe we'll let them take the exam. If you pass the trivia, you're good. If not now, you have to take the exam. It's more fun. That's why we're not in charge of education. It would be all messed up. We teach math. We don't decide the organization of it. Okay, so another fact, A times B, if you want to invert it, you change the order. B inverse times A inverse. Why? Because when you multiply A times B by B inverse times A inverse, that's when you get the identity, and again by the fact that the inverse is unique, right? We prove that it's unique. So if we find basically a form that plays the role of the inverse, that must be the only explanation. So A times B inverse times A inverse. We use parentheses to make it clear. From inside, we have B times D inverse. That must be the identity. A times the identity will, of course, be A. A times A inverse is the identity. Now, if you do it the other way around, it doesn't work out. So we learned that when you invert a product of two matrices, we flip the order. Is this clear? Do you have any questions so far? In case I'm going too fast. How about LU? If A is LU, of course, we can apply the same idea, and then inverse of A will be inverse of U times inverse of L. Now, we are not going to look into inverting triangular matrices, but it is in principle much simpler to invert a triangular matrix than just a regular matrix. Now, the utility of matrix inverse is that if we're dealing with a square system of linear equations, if I tell you AX equals B, You can have a closed form solution. Then X is A inverse times B. And then the problem is solved. Okay? That's by inverting A, we can essentially I can multiply both sides from left by A inverse, right? And I know this is the identity. Then I have X equals A inverse times B. Seems like a very straightforward to solve the problem. And probably it's okay for simple, small problems. Except it's a very bad idea. That's the worst idea ever you can come across in linear algebra. You should avoid inverting a matrix for solving a linear system at all costs. That's, whenever you do it, always think, is there any way I can avoid that? If there is, don't do it. Now, I'm not talking about a 2 by 2 or 3 by 3 matrices. Because you can verify easily. So one reason is that explicitly computing A inverse can lead to numerical instability. And that's very bad for numerical algorithms, especially larger scale when you are doing a lot of calculations and number multiplications. So it is much better to factorize the matrix to LU and use forward and back substitution. Another reason that it's extremely important in many practical problems, including robotic mapping, is that a lot of times the system of equations that we want to solve, the robot wants to build a map and collects all the measurements. That comes down to solving many times a system of linear equations. It's very large. But the system is sparse. I'm going to tell you in a bit what is a sparse. It has a very special structure that makes it possible to solve it fast. If you invert it explicitly, you will lose the structure. And it will become so hard to solve it that it's almost sometimes infeasible because computationally becomes intractable. Whereas if you don't invert it explicitly, we can factorize it and then use forward and back substitution to solve the problem. Now, a sparse matrix is a matrix. A sparse matrix is a matrix that has many zeros in its entries. All the white areas here you see are zeros. The gray, dark gray is some numbers, right? So I'm visualizing a matrix as a picture. When there is a zero, I'm just not visualizing anything. When there's a number, I am marking it with a dark gray point. So a matrix in principle is a picture when you plot it like this. And this is roughly a 500 by 500 matrix. 500, it's a little less than 500, but let's say 500 by 500. So 250,000 elements, entries in this matrix. Many of them are zeros. The number of non-zeros are 36,547. So most of the matrix are zero. This is A and is a sparse. Now we have sparse matrix libraries to store these in memory. You do not need to, so for sparse matrices, it is sufficient to store the address of that number and its value. So you don't need to store all the addresses for zeros. You just say row 300 and column 400, I have this value, right? If you list all of that, you will, given that most of the values are zero, you can store a very large matrix in memory very efficiently. So it's very important for larger scale problems. Now, as soon as you invert matrix A, you lose all of that. Now A is dense. So you have to do substantially more calculations. So a lot of libraries now, they do sparse, for example, LU factorization. So the factorization is such that it will preserve the sparsity, and then when you do forward and back substitution, you only calculate for things that are non-zero. So it's very efficient, substantially more efficient. Inverting it, this is a practical example, you will lose that. It will be, let's say roughly, if we can solve this in linear order, if you take a course in algorithms and data structure, they will teach you computational complexity. This will be cubic. So it will grow. One is growing linearly, the other one is growing cubically as the number of calculations that you need to do increases. So it's 500, for example, versus 500 raised to the power of 3 calculations. Make 500,000, make it 10,000. So one is growing so fast, cubically, that a lot of computers today will struggle with that type of calculation. Which is, by the way, it's a very good course to take to understand these concepts of computational complexity, data structures, and algorithms. Anyway, this is a main reason we don't invert A. Another one was for numerical stability, that there was a question in chat. What does it mean? What is numerical instability? That means we lose precision that we hold numbers, right? By doing divisions, for example, dividing by very small numbers. That will generate very large numbers. And we lose accuracy. If we do too many times during an algorithm, we might end up with numbers that are not accurate, are not reflective of the actual solution, because we have, not only we make them very large and very small by doing that, we have truncation as well. Maybe we hold up to 15 floating points. After many calculations, we end up with a result that is probably not accurate. There are some examples of that in the book. And one of your IA is recommending X370, learning about computers. It's pretty cool to learn how computers deal with these systems, regardless of your engineering discipline. I think these are general knowledge to have. All right, so here is a challenge for you. Can you invert a matrix without inverting it? Explicitly, don't invert it. I'm going to assume you have an equation to invert a matrix, or maybe you use Julia inverse to explicitly invert a matrix. So the problem is, can you do that by everything we learned about LU factorization, the identity matrix, forward and back substitution, but do not invert it explicitly, but calculate the inverse. So this will be the correct way to invert a big matrix and sparse matrix. I'm not going to solve it. But yeah, what's the idea?
Can you like set up like an AX equals B type thing? Where you, actually, I don't know if it would be like that, but where you have like whatever the initial A matrix is, something is equal to the identity matrix.
Right, given A, we want A inverse. That's the problem. And no, you're saying that can we use some form of linear system of equations? Yes, that's a good direction. And then you want to use LU. Of course, A can be LU. Now the question is how to set it up that produces the A inverse for us. Now what I'd like you to do is that try to solve it, at least the process of it, and then post it on Piazza. Let's form an answer on Piazza together. You can edit each other's answer. I hope you don't get in a fight over that. And this is very interesting. And then let's verify it in Julia. Now, when I do this in my code examples in the graduate class that I teach, most people are confused. What are you doing in this line? It's a matrix, / another matrix. I've never seen this in my life. Now, what they write in code, they say invert a matrix, right? That's avoid this always. So think about this problem. It's deeply connected to everything we talked about. It's a good summarization of everything we've done. Okay. So another topic that I want to talk about is the matrix transpose. The transpose takes rows of a matrix, turns it into a column. So very simply, if I have A, 1, 2, 3, 4 as a row vector, A transpose will be 1, 2, 3, 4, a column vector. That's the role of transpose. If I have B, 1, 2, 3, 4, 5, 6, B transpose will be 1, 2, 3, 4, 5, 6. So it takes a row, puts it in a column. Takes this row, puts it in a column. Second row, second column. And this is 3 by 2. Okay, so that's the matrix transpose. You can do it for vectors too. It will make a column vector, a row vector, it will make a row vector, a column vector. Okay? And that's called matrix transpose. Now, in general, the ij entry of A will be ji entry of A transpose. There's a second way of thinking about it too. Now in Julia, what you want to do is using apostrophe here. That's the transpose. That little thing here, apostrophe is the transpose. So I define A. A is a 2 by 3 matrix. I make the transpose of it, and I'm getting a 3 by 2. So I get 2, minus 2, minus 4, minus 6. I have it in this column. And I have minus 2, 1, minus 4, and I get it in the second column. So that's the role of a transpose. We will use it extensively in the future. Now, transpose has some properties. If you transpose a matrix and transpose it again, you get the original matrix back. No surprise, because it was a row, we put it in a column. Now we're saying that, oh, take the column, put it in a row. Well, we go back to where we started. So that's the first one. And another property of transpose is that it doesn't change the determinant. Just, this obviously is for a square matrix. Changing rows into columns will not change the determinant of a matrix. Just like the inverse, if you apply the transpose of two matrices to the product of two matrices, the order will be changed. Now, this is the only explanation if your matrices are rectangular, because otherwise you get dimension mismatch. However, it does make sense if both are square matrices. But that will not be correct because we know matrix multiplication is non-commutative. So the order will be different. We have more discussions around these topics in the book, and it's great if you look into them and ask your questions on Piazza. But for now, that's enough on transpose. And the last topic is revisiting permutation matrices. If you remember permutation matrices, the way we talked about them, we took an identity matrix, we said what rows we want to exchange, and then we would exchange those rows in the identity matrix that would produce P, the permutation matrix. For example, I want to send 3 to 1, 2 to 2, 5 to 3, 1 to 4, and 4 to 5. 3 to 1, the third row is in the first one. 1 to 4, you see here. We have a 1 here. 5 to 3, we get the fifth row here. I want to send 4 to 5, that's what I get. Okay, so, and 2 will not change, so we leave it to be the original second row. So by just playing with the rows of the identity matrix, we can generate P. We had an example of it before. And then, if you remember, we have multiplied it by the vector, and it did exactly this row exchange for us. Now, it is interesting that if you multiply a permutation matrix by its transpose, both from left and right, it will give you the identity matrix. Now, we know that the inverse of a matrix is unique, and this is very interesting that for permutation matrices, the inverse is the same as the transpose. Which makes it really convenient. If you want to invert a matrix, permutation matrix, just transpose it. Now you can easily verify this, right? Build a 2 by 2, 3 by 3 permutation matrix, or larger matrices, and then try it by hand in Julia. Transposing it will give you the inverse. Another interesting result here is that now if P times P transpose is the identity, let's just carry out some calculations based on what we learned today. I take the determinant of both sides. The determinant of the identity matrix is 1. The determinant of the product of matrices is the product of the determinant, right? Now, I know the determinant of P transpose and the determinant of P are the same. That was one property we learned today. So that will give me that the determinant of P squared must be 1. Now, the only explanation here is that P by construction is such that its determinant must be either +1 or -1. There is no other explanation. It is a very special matrix, and by construction, it gives you this property. And this is the way to prove it. Because once we know that its inverse is its transpose, we get this property. And that's the fact we used in the beginning to say that it's okay to divide by the determinant of P because it can only be 1 or negative 1, right? So this is the proof for that. You look confused. Just focus. That's good. Mind blown. This is really cool. That's actually, this is the proof for rotation matrices too, but we're not talking about it. Rotation matrices have exactly this property. Transpose of a matrix and a permutation matrix and its inverse, all of them in this example. So I'm going to define some reordering row exchange that I'd like to do. I want to have 3, 2, 5, 1, 4. That means I want to take 1, 2, 3, 4, 5 and change the order to 3, 2, 5, 1, 4. I'm putting this in a vector of indices here. I define my identity matrix here. Now this is very interesting. This I here, I don't know if you see the color. The color is green. It's not black like the other letters. Julia understands I is the identity matrix. Zeros, 5, 5 means make a matrix of 5 by 5, everything zeros, right? I don't want to create it one entry at a time. So make a matrix of all zeros here, 5 by 5. At the identity, what happens? The diagonal becomes 1. Now I'm passing the shuffling of rows here to the first reference of P. And I'm use the old columns. So what happens? I'm just exchanging rows. There's a few lines are good to practice. Try to make sense of it. It's very compact, but what I'm doing, I'm exchanging rows. Now, then I'm going to try P multiplied by P transpose. And that gives me the identity matrix, which that's exactly what we expect. Okay? So it's a very compact code, maybe a lot to take. But take your time, think about it, and ask your questions. And try to solve that problem on Piazza. And next time, we're going to start talking about vector spaces. And you can find about vector spaces part 1 in chapter 7 of the book. Okay, that's it for today, and see you next time.